The asteroid belt, gateway to riches or a deadly trap. Part 1. Myths of a crowded asteroid field. For generations, popular culture has painted a vivid picture of the asteroid belt as a treacherous, densely packed region of space. Imaginations fueled by science fiction often depict starships dodging countless hurtling rocks, a perilous gauntlet for any interstellar traveler. This pervasive image of a cosmic demolition derby has deeply ingrained itself in the public consciousness, shaping our understanding of this fascinating celestial neighborhood. However, the dramatic portrayals often diverge significantly from the actual scientific reality. The true nature of the asteroid belt is far more subtle and, in many ways, even more intriguing than the fictionalized versions we have grown accustomed to. The cinematic portrayals, while thrilling, frequently sacrifice accuracy for dramatic effect. Scenes of heroes skillfully maneuvering through a dense swarm of asteroids create palpable tension, but misrepresent the vast emptiness of space. This misconception, though entertaining, can obscure the genuine challenges and wonders of exploring such an environment. Understanding the origins of these popular myths is crucial to appreciating the true scientific understanding of the asteroid belt, a region that holds profound clues to the early history of our solar system. The allure of the unknown often leads to exaggerated imagery, but a closer look reveals a different kind of marvel. This romanticized view has perhaps made the asteroid belt seem more exciting, yet it also trivializes the sheer scale of the cosmos. If the asteroid belt were truly as crowded as often depicted, interstellar travel would be even more impossibly difficult. The continuous bombardment would pose an existential threat to any spacecraft, making safe passage a near impossibility. This dramatic exaggeration, while fueling narratives, overshadows the profound scientific questions and potential resources that this region truly represents. It's a testament to the power of storytelling, but also a call for scientific clarity. The notion of a densely packed asteroid field can be traced back to early science fiction literature and films that needed a visually engaging obstacle. It's a powerful narrative device, making voyages through space feel more perilous and exciting. These early depictions often predated detailed telescopic observations and spacecraft missions that later revealed the true distribution of objects within the belt. The convenience of a cluttered environment for plot purposes outweighed the emerging scientific understanding, solidifying a myth that persists even today. It's a classic example of fiction shaping perception. Consequently, many people harbor a mental image of the asteroid belt as a literal minefield, a place where collision is not just probable, but almost inevitable. This makes the prospect of asteroid mining or establishing outposts seem even more hazardous than they actually are. While risks certainly exist, they are not primarily driven by the density of objects, but rather by the immense distances and the challenges of rendezvous. Dispelling these myths is the first step towards a more accurate and scientifically informed appreciation of the asteroid belt's true character and its potential. Part 2. Reality of vast distances between rocks. In stark contrast to the popular imagination, the reality of the asteroid belt is one of immense, almost unfathomable emptiness. Far from being a chaotic jumble of closely spaced rocks, the average distance between significant asteroids is staggering. If one were to stand on an asteroid within the main belt, the next largest object would likely be hundreds of thousands or even millions of kilometers away. This vastness makes accidental collisions between spacecraft and asteroids exceedingly rare, a far cry from the dodgem scenarios often portrayed on screen. Imagine scaling down the entire asteroid belt to the size of a football field. On this scale, the individual asteroids, even the largest ones, would be no bigger than grains of sand, separated by many meters or even tens of meters. This analogy helps to visualize just how sparse the distribution of matter truly is within this enormous volume of space. Traveling through the asteroid belt is more akin to navigating an ocean with a few scattered islands than traversing a dense forest. The primary challenge is not avoiding obstacles, but finding them. The sheer volume of space encompassed by the asteroid belt is truly immense, stretching for hundreds of millions of kilometers between Mars and Jupiter. Within this colossal region reside millions of asteroids, ranging in size from pebbles to dwarf planets. However, when these numbers are divided by the volume, the resulting density is incredibly low. This mathematical reality underscores the emptiness, demonstrating why missions like Dawn and OSIRIS-REx could navigate the belt with relative ease without constant evasive maneuvers. For a spacecraft, the probability of hitting an uncatalogued asteroid is remarkably low. The greater risks come from micrometeoroids, tiny dust particles that, despite their size, can cause significant damage at hypervelocity speeds. These microscopic threats are ubiquitous throughout the solar system, not just concentrated in the asteroid belt. The perception of risk is often misplaced, focusing on large, visible objects rather than the more insidious, smaller ones. This requires a shift in engineering focus for spacecraft design. Therefore, the main challenge for asteroid exploration or future mining operations is not avoiding collisions, but rather locating and reaching specific target asteroids. Each mission requires meticulous planning and precise trajectory calculations to intercept a chosen object, a process that can take years. The belt is less a barrier and more a dispersed repository, demanding sophisticated navigation and patience. This understanding is crucial for moving from fictionalized encounters to practical space endeavors. Part 3. Theories of a Shattered Planet. One of the most enduring theories regarding the origin of the asteroid belt posits that it is the remnant of a shattered planet. This hypothesis suggests that a celestial body, once orbiting between Mars and Jupiter, underwent a catastrophic collision or was torn apart by powerful gravitational forces. The debris from this cosmic cataclysm, instead of coalescing back into a single body, then spread out to form the myriad of rocks and dust we observe today in the main asteroid belt. This idea has captivated astronomers for centuries. However, modern planetary science has largely moved away from the idea of a single, destroyed planet. The combined mass of all asteroids in the belt is surprisingly small, less than 4% of Earth's moon. If a planet once existed there, it would have been a rather diminutive one, perhaps comparable in size to Ceres, the largest object in the belt. This low total mass makes the shattered planet theory less plausible, as it would require an initial planet of significantly greater mass to account for the current distribution. Instead, the prevailing scientific consensus points to a different narrative. The asteroid belt represents primordial material that never fully coalesced into a planet. In the early solar system, as planets were forming from a swirling disk of gas and dust, the region between Mars and Jupiter was subject to intense gravitational perturbations from the nascent gas giant Jupiter. Jupiter's immense gravity acted like a cosmic stirrer, preventing the smaller planetesimals in this region from smoothly accreting into a larger body. These gravitational disturbances repeatedly disrupted the formation process. Instead of steadily growing through gentle collisions, the planetesimals in this zone experienced more energetic encounters that often resulted in fragmentation rather than amalgamation. This continuous grinding and scattering prevented the formation of a single, coherent planetary body. The asteroid belt, therefore, serves as a fossilized record of these frustrated planetary formation attempts, a testament to Jupiter's profound influence. The diverse compositions of asteroids, ranging from rocky S-types to carbonaceous C-types, also argue against a single parent body. Such varied materials suggest different formation conditions and origins within the protoplanetary disk. If the belt were once a single planet, one would expect a more uniform composition, or at least a clear differentiation into core, mantle, and crust materials. The current understanding paints a more complex picture of scattered remnants from various formative processes. Part 4. Ceres, the dwarf planet of the belt. Ceres stands as the undisputed monarch of the asteroid belt, not just the largest asteroid, but officially classified as a dwarf planet. With a diameter of approximately 940 kilometers, it accounts for roughly a quarter of the entire asteroid belt's mass. This considerable size grants Ceres enough self-gravity to pull itself into a nearly spherical shape, a defining characteristic that elevated its status from a mere asteroid to a dwarf planet in 2006, alongside Pluto and Eris. Unlike the irregularly shaped asteroids that dominate the belt, Ceres' roundness hints at a complex internal structure. Scientific data from the Dawn mission revealed that Ceres is not merely a uniform rock. It possesses a differentiated interior, likely consisting of a rocky core, a mantle of ice, and possibly even a subsurface ocean of liquid water. This internal layering is a hallmark of larger, more geologically active bodies, and makes Ceres a truly unique object in the inner solar system. The presence of significant quantities of water ice is one of Ceres' most compelling features. Spectroscopic observations and data from the Dawn spacecraft detected water molecules and hydrated minerals on its surface. This ice, along with tantalizing bright spots observed within its craters, suggests active cryovolcanism, where icy brines might periodically erupt onto the surface. Such activity implies an internal heat source, potentially fueled by radioactive decay or tidal forces. These findings make Ceres an incredibly important target for astrobiological research. The combination of water, organic molecules, and a potential internal heat source raises the intriguing possibility that Ceres could harbor conditions suitable for microbial life, either now or in the past. It represents a potential oasis in the otherwise arid inner solar system, a place where liquid water might persist beneath a protective icy shell, shielded from the harsh vacuum of space. Studying Ceres offers invaluable insights into the early solar system. As a primordial dwarf planet, it likely retains much of its original composition from the time of planetary formation. Its surface features, internal structure, and volatile content provide clues about the conditions prevalent in the protoplanetary disk billions of years ago. Ceres is a living fossil, offering a window into the building blocks that form the larger planets. Part 5. Vesta and Giant Impacts. Vesta, the second most massive object in the asteroid belt, stands in stark contrast to its larger neighbor, Ceres. Unlike the icy, spherical dwarf planet, Vesta is a dry, rocky protoplanet, an irregularly shaped world that bears the scars of colossal impacts. Its unique composition and history make it a crucial object for understanding the processes of planetary formation and the violent collisions that shaped the early solar system. Vesta is a survivor of epic cosmic battles. Vesta is distinguished by a gigantic impact basin named Rhea Silvia that dominates its southern hemisphere. This colossal crater spanning approximately 505 kilometers in diameter, is so massive that it nearly encompasses the entire asteroid. The impact that created Rhea Silvia was an event of staggering energy, so powerful that it excavated vast amounts of material from Vesta's interior, blasting it into space. This single event dramatically reshaped the protoplanet. The material ejected from the Rhea Silvia impact is not lost to us. Scientists have identified a significant family of smaller asteroids, known as Vestoids, which share a similar spectroscopic signature to Vesta. These Vestoids are believed to be fragments that were blasted off Vesta during the Rhea Silvia event. Some of these fragments have even made their way to Earth as meteorites, providing scientists with direct samples of Vesta's deep interior without ever having to travel there. The study of these HED, Howardite Eucrit Diogenite meteorites, coupled with data from the Dawn mission, revealed that Vesta is a differentiated body. This means it has a distinct metallic core, a rocky mantle, and a crust, much like Earth and other terrestrial planets. Vesta is essentially a tiny, rocky planet that almost formed, but its growth was stunted. Its differentiation indicates it melted early in its history, allowing heavier elements to sink to the core. These giant impacts, particularly the one that formed Rhea Silvia, highlight the violent nature of the early solar system. Collisions were not rare occurrences, but fundamental processes that governed the growth and destruction of nascent planetary bodies. Vesta serves as a prime example of how these catastrophic events could reshape entire worlds, create new asteroid families, and even deliver pristine samples of extraterrestrial material directly to our planet. Part 6. The Dawn Mission Discoveries. NASA's Dawn mission, a pioneering endeavor, dramatically reshaped our understanding of the asteroid belt by becoming the first spacecraft to orbit two distinct extraterrestrial bodies, Vesta and Ceres. Launched in 2007, Dawn employed an innovative ion propulsion system, allowing it to execute an unprecedented orbital tour, first around Vesta from 2011 to 2012, and then around Ceres from 2015 until the mission's end in 2018. Its scientific payload included cameras, a visible and infrared mapping spectrometer, and a gamma-ray and neutron detector, providing a comprehensive suite of tools for detailed analysis. At Vesta, Dawn's instruments mapped the asteroid's complex topography, confirming its differentiation and revealing the colossal Rhea Silvia basin in exquisite detail. The mission provided conclusive evidence that Vesta is a true protoplanet, a surviving relic from the earliest stages of planetary formation. It also helped to link Vesta directly to the HED meteorites found on Earth, allowing scientists to piece together a more complete picture of its internal structure and geological history. Dawn showed Vesta to be a dry, ancient world, battered but remarkably preserved. Moving to Ceres, Dawn uncovered a world far more complex and active than initially imagined. The mission revealed Ceres to be rich in water ice, with evidence of hydrated minerals across its surface. The most striking discovery was the bright spots within Akator crater, later identified as highly reflective salts, primarily sodium carbonate, left behind as briny water evaporated from below the surface. This indicated ongoing geological activity, driven by subsurface liquids, making Ceres a compelling object for astrobiological study. Dawn's data also indicated the presence of organic molecules on Ceres, adding another layer of intrigue to its potential habitability. These complex carbon-bearing compounds suggest that Ceres may have been capable of synthesizing or preserving the chemical building blocks of life. The mission provided strong evidence for a subsurface ocean, possibly still liquid in places, further enhancing the prospects for finding primitive life, or at least the conditions that could support it. The Dawn mission unequivocally demonstrated the vast diversity within the asteroid belt, revealing two dramatically different worlds that formed in the same cosmic neighborhood. Vesta, a dry, rocky protoplanet, and Ceres, an icy, geologically active dwarf planet, offer a snapshot of the varied fates of planetesimals in the early solar system. Dawn's findings continue to be analyzed, providing invaluable insights into planetary evolution, water distribution, and the potential for life beyond Earth. Part 7. Mining Dreams of Metals and Water. The asteroid belt, despite its vast emptiness, represents an immense repository of valuable resources, fueling dreams of future space mining. Among the most coveted materials are precious metals like platinum, palladium, and rhodium, which are far scarcer on Earth's surface, but believed to be abundant in certain types of asteroids. Additionally, the belt holds vast quantities of water ice, a resource even more crucial for supporting human expansion into space. These extraterrestrial riches could revolutionize industries both on Earth and in orbit. Platinum group metals, essential for electronics, catalysts, and advanced technologies, are primarily concentrated in M-type asteroids, which are thought to be the exposed metallic cores of larger, differentiated protoplanets. Extracting these metals could alleviate scarcity on Earth and provide materials for constructing advanced space infrastructure. The sheer volume of these resources in the asteroid belt dwarfs Earth's entire known reserves, offering a virtually limitless supply. Even more critical for establishing a sustained human presence in space is water. C-type asteroids, particularly carbonaceous chondrites, are rich in water-bearing minerals and ice. This water can be processed into breathable oxygen and rocket fuel, hydrogen and oxygen, transforming space exploration by removing the need to launch these heavy consumables from Earth. Imagine refueling stations in orbit, supplied by water mined from asteroids, making trips to Mars and beyond far more feasible and economical. The technical challenges of asteroid mining are, however, immense. Developing the propulsion systems to reach these distant objects, the robotics to extract materials in zero gravity, and the infrastructure to process and transport them back to Earth or orbital depots will require monumental technological leaps. The initial investments would be astronomical, but the potential returns, both economic and strategic, could be revolutionary, reshaping global economies and opening up the solar system. Beyond material wealth, asteroid mining offers a pathway to sustainable space exploration. By utilizing resources found in space, humanity can reduce its reliance on Earth-based launches, making ventures further into the solar system more environmentally friendly and cost-effective. The asteroid belt could become humanity's first extraterrestrial quarry, providing the raw materials to build a multi-planetary civilization, transforming science fiction into tangible reality. Part 8. Science fiction visions of asteroid colonies. Science fiction has long envisioned the asteroid belt not just as a source of raw materials, but as a future home for humanity. These narratives often depict vast, self-sufficient colonies carved directly into larger asteroids, protected from radiation and meteoroid impacts by kilometers of rock. These subterranean cities would represent humanity's first true steps towards becoming a multi-planetary species, offering a new frontier for civilization and a refuge from an overpopulated Earth. In these visions, asteroids are transformed into spinning habitats, generating artificial gravity through centrifugal force. Picture immense tunnels and chambers lit by artificial suns, where generations of humans live and work, far from Earth's gravity well. These colonies would be designed for long-term sustainability, recycling all resources and growing their own food, forging a unique culture distinct from their terrestrial origins. They would be self-contained worlds, microcosms of humanity's future. Such asteroid colonies are often portrayed as hubs for industry, particularly for asteroid mining and manufacturing in zero gravity. The resources extracted from the belt would feed these orbital factories, producing everything from new spacecraft to advanced materials. This industrial ecosystem would create a powerful economic engine, driving further expansion and innovation, establishing the asteroid belt as a crucial economic and strategic region of the solar system. Beyond the practicalities, asteroid colonies in fiction often explore themes of independence and self-governance. Far from Earth, these communities might develop their own political systems and cultural identities, sometimes leading to conflict with Earth-based authorities. This narrative arc delves into the sociological implications of space colonization, questioning what it means to be human when disconnected from the ancestral planet. While purely fictional now, these visions serve as powerful inspirations for real-world space agencies and entrepreneurs. They illustrate the long-term potential of the asteroid belt, pushing the boundaries of what is considered possible. The challenges are immense, but the dream of living among the stars, nestled within an asteroid, continues to fuel imagination and scientific endeavor, moving us closer to making these science fiction visions a reality. Part 9. Hazards of Asteroid Exploration. Despite its allure, the asteroid belt presents significant hazards to exploration and future colonization efforts, far beyond the mythical crowded field. The primary dangers stem from the immense distances, the harsh radiation environment, and the persistent threat of micrometeoroid impacts. These challenges require advanced engineering, meticulous planning, and robust spacecraft design to mitigate the risks to both robotic probes and human missions. The sheer remoteness of the asteroid belt means that missions are inherently long duration, placing immense strain on spacecraft systems and requiring unprecedented levels of reliability. Communication delays, due to the vast distances, can stretch to tens of minutes, making real-time control impossible. This necessitates sophisticated autonomous systems capable of responding to unforeseen events without immediate human intervention, adding complexity to mission design. The region between Mars and Jupiter lies beyond Earth's protective magnetosphere, exposing spacecraft and potential human occupants to high levels of cosmic radiation and solar energetic particles. This radiation can damage electronics, degrade materials, and pose severe health risks to astronauts, including increased cancer risk and acute radiation sickness. Shielding requirements for long-duration human missions would be substantial, adding significant mass and cost. While large asteroid collisions are rare, the belt is still home to countless micrometeoroids, tiny particles traveling at extremely high velocities. Even dust-sized particles can inflict significant damage upon impact, gradually eroding spacecraft components, degrading solar panels, or even puncturing sensitive equipment. Protecting against this continuous barrage requires multi-layered shielding and resilient systems, a constant design challenge. Furthermore, the very nature of asteroids, their irregular shapes, low gravity, and often chaotic rotations, poses challenges for rendezvous, docking, and surface operations. Landing on or anchoring to a small, tumbling asteroid is a complex feat, requiring precise navigation and specialized robotic tools. Each asteroid is unique, demanding adaptable strategies. These hazards underscore the difficult but rewarding nature of humanity's journey into the asteroid belt. Part 10. The belt as a key to solar system history. Far from being merely a collection of cosmic rubble, the asteroid belt is a celestial archive, a pristine record of the early solar system's formation and evolution. Unlike the planets, which have undergone significant geological processing, differentiation, and atmospheric changes, many asteroids have remained largely unaltered since their formation billions of years ago. They are time capsules, preserving the original building blocks from which the planets were made. The diverse compositions of asteroids, from the carbon-rich C-types believed to be primitive, water-bearing material, to the rocky S-types and metallic M-types, provide a chemical inventory of the protoplanetary disk. By studying these varied compositions, scientists can infer the conditions, temperatures, and chemical gradients that existed in different regions of the early solar nebula. This helps to paint a detailed picture of the chaotic environment where our solar system was born. Asteroids also offer clues about the migration of giant planets. Theories suggest that Jupiter and Saturn may have migrated inwards and then outwards during the solar system's early history, scattering and mixing the asteroid population. The current distribution and orbital characteristics of asteroids can be used to test these planetary migration models, providing insights into how the architecture of our solar system evolved over time. Furthermore, the asteroid belt is a source of extraterrestrial material that regularly falls to Earth as meteorites. These meteorites provide direct physical samples of asteroids, allowing scientists to analyze their mineralogy, isotopic ratios, and organic compounds in terrestrial laboratories. This free sample return enhances our understanding of asteroid compositions and links specific meteorite types back to their parent bodies in the belt. In essence, the asteroid belt is an invaluable resource for understanding the origins of our solar system, the processes of planet formation, and even the delivery of water and organic molecules to early Earth. It is a cosmic laboratory where fundamental questions about our existence can be explored. Every rock, every crater, every faint spectral signature within the belt tells a piece of the story of how our planetary home came to be.